sorry, I only speak English or French or German, but I think you prefer English. And I hope, thank you, Robert, for that nice introduction. And I hope you've understood a lot. But anyway, I'll go through this quite quickly, I think. And then if you have questions, please ask questions and we can stop or discuss details. But I'll go through quite quickly because you're quite an educated panel here today. But what I want to show you is the trouble we go to make accurate loudspeakers. And when I mean accurate and precise, it's to reproduce natural sounds and to make them sound as natural as possible. So that's the first thing. Then I'd like to also explain that the second most, or the first, I'm not sure, most important element in sound reproduction is the room. And the room contributes to a lot of the listening quality. And then we'll look at a few, and then I'll sort of explain that the main problems in a room are the low frequencies, and then we'll look at a few solutions to treat low frequencies, and one of them is an active sound absorber that goes between 15 and 150 hertz. That's the main of the problem. So that's basically what we're going to cover today. So I'll start off just with a few dimensions in sound. You all know that sound is pressure vibrations in air going from 20 hertz up to 20,000 hertz. That's what we can hear. They all travel at approximately the same speed. That means that the wavelengths are very different, going from about this length for 20,000 hertz to about 1.5 times the length of this room for 20 hertz. So we have to deal with very different wavelengths, and the pressure is very, very low, okay? It's nothing to do with atmospheric pressure or any pressure difference you get when you open a door. But we can hear from 0 dB to 120 dB is where we start not enjoying listening anymore because it's too loud. But 0 dB is 0.0002 Pascal, and Pascal is a really small element, and that corresponds in terms of water column to 0.02 microns of water column. So you're kind of molecular type of width and stuff. Okay, then 80 dB, that's kind of normal listening environment. That corresponds to 0.2 Pascal, and that's 100th of a millimeter water column. Okay, so that's extremely small, and that corresponds to about 20 millimeters air column. So the difference in atmospheric pressure between here and here. So if you go up and down 100 times per second, you could hear 100 hertz at 80 dB. So, and all this, you can hear this on top of the natural variations of the atmospheric pressure with somebody moving in the room, a door opening, wind, or anything else. So this is just to show that our ears are extremely sensitive to variations in pressure. And the other thing is that all these variations in pressure that we hear sounds, the vibrations that come from all over the place, they all get mixed up, and the only thing that we can sense is pressure variations. And then our brain will analyze this, decompose it into frequencies and phase and everything to determine what the sound is, where it's coming from, and what type of environment we're in. So this is things that is impossible to do with light. When you see white light, all the frequencies are mixed up together and you can just see it. It's difficult to see where it comes from. You get a bit of reflection. But our ears are extremely sensitive measurement instrument or sensing instrument, and our brain is extremely sophisticated way of analyzing all this information. Okay. Now, reproduction of sound, we try and reproduce sound as accurately as possible, and anything that changes the accuracy we call distortions, and there's lots of different types of distortions, you know that well. There's linear distortions that are the same when you put the volume up or down, put the pressure up or down, that can cover all the range of frequencies or some of it. And then there's non-linear distortions that will change certain elements of it. But there's a lot of quite useful tools that you can see also and illustrations of different types of of distortions that you can find on internet. So it's interesting to go through. Just a way of illustrating a distortion is something like this, spatial distortion. You can have coloration that can affect certain points of your sound or affect more all of it. And it's just important to get aware, because if you live in some color like this, it just starts to become normal, and you think that's normal to see everything yellow, and your brain adjusts to it and it thinks it's normal. Okay. Here in the chain of reproduction, sound reproduction, you've got microphones, so captation of sound, then you've got your kind of processing, loudspeakers and room, and this just goes to show that most of the distortions come in from, well, when you cap the sound, recording, and then a lot of them come from the loudspeaker and the room, and that's where the key elements are, where you have to be careful of distortions and keep watching them. Okay. Then there's our expectation of the sounds also, so this you can't measure. If you measure with a microphone you can't, but our expectation of the sound does change the way we perceive the sound, okay? And this is psychoacoustics, and this is very important to understand. It is our brain makes a picture of what we hear, what we see, the environment, and it takes information from what you hear, what you smell, what you see, what you feel, and everything, and it makes one picture. And sometimes it's difficult to differentiate what part of the picture comes from sound and what of it comes from what you see. And just an example here of how our brain builds up the expectation, which one is darker and which one's lighter. It looks, you would say, that the B is much lighter than the A, but they're both exactly the same color, which you can see here with the same band, the same color going through, and there's no difference here, there's no difference here. But your brain says, aha, but this is black, white, black, white, black, white, and then there's the shade of this element. So it builds in already, and it says this one is lighter than this one, which it does. You perceive it as lighter, but it's not at all. And the same things happen with sound also. And I'll just illustrate a few things here. So here's a recording. I don't know if you've heard this one, but it's a recording. There's two kind of messages in it, and you can either hear one or the other, depending on what you're focusing on. So I'll just play it.
Yeri, 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 yeri.
How many people hear Yanni? 2. How many people hear Laurel? Okay, it's funny because yesterday we did the same exercise in a class where people were on average much younger than you. And I think 90% or 80% of the people could hear Yanni and the other ones. So basically there's Yanni, Yanni, and then there's Laurel, Laurel. So if you're focusing on the low frequencies, you'll hear Laurel. And if you're focusing on the high frequencies, you'll hear Yanni. So it's quite interesting that whatever you focus on, you can hear something, and then you sort of adjust to that, and you're going to be hearing those range of frequencies. That was the first one I wanted to show you. Next one is also a very good example to show. I'll just play it. So. Ba, 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 ba. What do you hear? Ba, 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 ba. What do you hear? Close your eyes. Ba, 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 ba. The second one. Ba, 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 ba. The sound is exactly the same sound in both. Our brain builds an image of what we hear, judging on taking information from what we see and what we hear. For me, this is a very powerful proof that what you see influences what you, maybe not what you hear, but what you perceive. Now, one more example.
To this.
Listen to this.
Sounded strange, right? Have a listen again and see if you can get anything. Still strange. Now listen to this.
I think Brexit is a really terrible idea.
Which I do. So you heard some words there, right? Now listen to the first sound again. I'm just going to replay it. Yeah? So you can now...
So yeah, this is a very, I recommend you look at the whole of his video because it's very powerful, and it's Seth. But anyway, this also shows that what you've understood and what you've already kind of adjusted to, you can hear also a lot better, which is the case with most of you sound engineers. Anyway, that was just to show that you have to trust your ears, but it's very important to know what you're hearing and know what you're seeing. And as sound engineers, you learn to focus more on what you're hearing than what you're seeing, and to be able to adapt to both. Now, sound reproduction mainly goes through loudspeakers, so I'm going to just explain all the trouble that we have to go through to make accurate loudspeakers. First of all, the role of an audio monitor is to transform an electric signal into an acoustic signal as accurately as possible, and no more and no less than that. I hope we all agree on that. We don't make beautiful sound, we're not creative, we just have to reproduce an electric signal into an acoustic signal with the least possible distortion and recreate the natural sound again, or the sound that the engineer and the author of the acoustic message wanted. So now there's different, so sound is pressure going up and down. That's what we hear. That's what we try and reproduce. To reproduce pressure, you have to kind of compress the air a little bit, and it's the acceleration of the particles that create the pressure. So we try and recreate acceleration to create the pressure. There's different ways of doing it, but the most common is this standard loudspeaker, the standard driver, or the transducer. We can do it with electrostatic systems and different ways, but this, especially in low frequencies, when you have to move a lot of air, it's definitely the most common. Everybody understands basically how this works, but there's a coil here that's in a permanent magnetic field, and when you put electricity through going in one way, it'll induce some magnetic field that will, in conjunction with the permanent magnetic field, will push the coil up or down. So linked to this coil, well, you have a surface, this kind of area, a membrane that will move back and forth. Then there's what you call the dust cap that closes this. And then all of this has to come back. If there's no more electricity going through, it has to come back to its neutral position. So you need to have some springs that bring it back to its position. So you have the spider and you have this surround that bring it back into its position. You also have a spring here, a bit of a spring that's the air inside this element. It can be open or not here, but you have all these elements here. So there's lots and lots of, it's quite simple, but there's an enormous amount of characteristics and parameters that go into it that define all the components, like this membrane, the surround, the rigidity even here, the dust cap, how powerful the magnet is, of course the area. So there's a lot of characteristics in these that are quite complex. And normally they're all summarized in these Thielen small parameters. I think you've all heard of these, and there's probably 10 important ones and 25 or 30 in all of them. But it's all has to be balanced together. You can't just take a magnet and take this and just put it all together and think that it's going to work. It all has to be kind of calculated and planned, and everything has to work together. How long this coil is it long, is it short, when it goes out, what the path is, if it goes out or in. There's lots and lots of different elements that go into here. To make this move, well, we have to amplify the signal somewhere. Okay, so the amplifier can be outside or it can be inside. For the last 25 years, we've been making only active speakers. That means that the amplifier is inside, and the reason is that you can adapt the amplifier exactly to this mobile mass and that it's driving. So it's a lot more efficient, and you can make it a lot more accurate. This is like when you buy a car, the engine's in the car. You're not going to buy a car and then buy an engine that's trailing sort of 100 meters behind. So that's kind of the idea that we have. And then you can adapt it to this membrane. And this membrane, of course, this is also, as we saw, it's a mobile mass on springs, okay? And of course, it'll move differently at different frequencies. So each one of these drivers will be quite good at reproducing a certain range of frequencies, but not more than that. And then there's the mechanical filters and that roll off the low ends and the high ends. And of course, where it's not very efficient at reproducing sound, there's a lot of distortion, okay? Here you can see, so this Q factor, you can think of this as distortion. And then there's the phase. So, phase, you understand. I think Robert explained a little bit. But basically, when you have high frequencies or low frequencies all together that leave, like in a snare drum, that'll go ta. You'll have the high and low frequencies will all leave the drum at the same time and reach your ear at the same time. Unfortunately, any type of signal that goes through any type of filters will be affected, and the low frequencies will be slowed down compared to the high frequencies. So if you go through any type of filter from a ta, you'll end up with something that's more like t-a, where the low frequencies of the a are delayed compared to the high frequencies of the t. So this is important to keep it. And then, so very little bit, not much. You probably won't even notice it in some frequencies. And it's also, the phase is also very important to locate where the sound is coming from. So we're quite sensitive to phase when locating the sound, especially with impacts. If you have a sine wave, you have two sine waves that are playing. It's difficult to say if they're in phase or not. It's just continuous there. You can't really tell. But when there's an impact, you can tell the difference. And you're sensitive to phase. Well, you've got about 20 centimeters between your ears. So when the wavelength is 17 meters, 20 centimeters is not a big difference. So you won't really hear the difference in phase, okay? So there you'll be more sensitive. Well, it's very omnidirectional, these low frequencies. High frequencies, again, 20,000 hertz, you have wavelengths this size. In 20 centimeters, there'll be lots of different cycles, so you won't be able to analyze the phase. So normally, you can say you're sensitive to phase between around 200 to 300 hertz up to 2,000-3,000 hertz. That's where you're sensitive. But anyway, it's normal to have a bit of, so this is a kind of the filter that comes from the all pass of the device itself. There's nothing much you can, not the all pass, the high pass of the driver itself. There's nothing much you can do about that. That's the physical construction of this driver. Okay, so here we see that it's not perfect. There's still a lot of things you can improve. The first thing is the bandwidth. So you want to go higher. So here you can add another driver that's perfectly adjusted to these higher frequencies, and then you have to have a crossover filter that makes sure that what comes out of here and here is totally flat, and you get a good response. I think Robert explained that. This filter you have one, this amplifier is not perfectly adapted to this driver or this driver. It's adapted to both, but there'll be quite a bit of it. So here, in between where the crossover is, you'll have quite a bit of distortions because none of the drivers are perfectly adapted to that frequency. And then, of course, this filter will add phase rotation here that you don't really want either. But you can get some high frequencies. That is good. Now, low frequencies. Oh, no, sorry. So one of the ways of getting less distortion here is to have two amplifiers that each one is perfectly adapted to the membrane it's driving, okay? So that you can have the filters before, and this is what you call an active crossover, yeah? And then you have each driver's got its own amplifier. That's also the common way of doing things now. Then low frequencies, well, either you can add more woofers, you can add more of them, but you can also, if you have a closed cabinet, you're going to only use the energy that comes out of the front and not out of the back. So you can use the energy that comes out of the back, but you have to kind of make sure that it comes out again as a lower frequency that's perfectly adapted to what comes out of the front. So what we do is we build a resonator with the cabinet and make sure the resonator resonates at exactly the right frequency that will complement what comes out of here. Okay, so it's a resonator. A resonator is, again, mass on springs. So here we have the mass that is the air inside here, and the spring is the air inside here, and it's activated by the back of the membrane. So just as a basic rule of thumb, if you don't have, this allows to use the energy from the back to extend the bandwidth down below, in the low end. If you don't have a ported cabinet or a bass reflex, you need 3 times the surface. So typically you'd need 3 times the amount of drivers. In studio monitors, you try and keep the monitors quite small, powerful, full range, so we use this quite commonly. What's very important is that it's perfectly adapted, and what comes out of here, here, and here is flat in frequency and flat in phase. And often when you have ported systems or bass reflex, you have a hole and then you have a big bump, so that's what people don't like. Or you have a much too big a distance between here and here, so there's a bit of delay, and that's what you don't like. But it has to be done properly. And then bass reflex, of course, this mass here, you can use that, or you can use another passive driver that resonates also. That makes it a bit easier, but it's not quite as good with the inertia that's built into the system. Okay, so this is quite commonly used, and if it's well dimensioned, it works very well. Now we still have a few other problems. One of which is this distortion. Most of the distortion comes, as I said, is the driver as a membrane mass on springs, and it won't move at the same speed at all frequencies. So it's got its resonance frequency, it's got the resonance frequency of the material itself, of the suspension and all this. So basically, if you push it the same way, it's not going to react the same way. So we have a feedback loop that goes from that measures the speed of the coil inside the magnetic field, and this feeds back information in real time back into the amplifier and adapts the output impedance of the amplifier so that it adjusts the speed. Okay, so here, well, you can see kind of the schematic here, but there is an EQ here, or it is different for all the frequencies. So it basically corrects all the physical characteristics of the membrane to make sure that everything is flat and there's no coloration. So everybody thinks that it's what the driver is made of that makes the sound. Not at all. Whatever the driver is made of, it shouldn't sound anything. It shouldn't sound. It should just reproduce the sound. So all this ringing that comes from the material itself should be kind of filtered out or compensated for. So this basically allows that you can accelerate and brake and stop and have as much dynamic as possible in this without overshooting, without creating secondary vibration. So no coloration whatsoever. Okay, and this we do on all our drivers. And this is basically the schematic you have of it. Then there's one more problem, it's the phase. And here, if you want a phase neutral loudspeaker, that means that the phase is the same from the signal that comes in here and the acoustic signal that comes out here. You need to compensate for everything that happens in here, yeah, so that you can hear what comes in. So we compensate the phase here. So it basically, you use all-pass filters, or you have to slow down the high frequencies to wait for the low frequencies, and then they all come up at the same time, as Robert explained. So we do this with all-pass filters that are all analog, and that look something like this. And yeah, all-pass filter is a filter that's going to affect the phase in certain frequencies without affecting the frequency response. Yeah, so this will have this kind of response, and you need lots of these filters to come back to a linear phase response. So linear phase response, this is what you call. So the phase is like this, and you want it linear, and basically it can be like this or like that. That's just a time delay factor, and that's the same. So yeah, so if it's linear phase, so of course if you go back half a meter, there'll be a phase rotation that longer, but on the high frequency, but that's linear, so that's not a problem. But you want it coming back out the same at the same time. So we're looking for a linear phase response. And then you can have a linear phase response that goes down very low, down to 20 hertz, but the problem is you're going to have to wait a long time. Or you can have, and that creates a lot of latency in the system. So what we basically, latency in the system is not a problem when you're listening to music. You press play, you can wait for 3-4 seconds until the music comes out. It's not a problem as long as it's all coming out at the same time. But when you're recording, when you're mixing, when you're doing post-production, you can't have too much delay, and normally it's recognized that 1 millisecond is kind of the maximum latency you want in your loudspeaker. 1 millisecond is again 35 centimeters approximately, moving back or forward. So it's not that much. But we've limited ourselves to half a millisecond, and we can correct the phase here down to 150 hertz. Okay. So, oh yeah, I've moved that. Yeah, just here, just coming back a little bit on the different types of cabinets that can be closed, bass reflex, plan, or a longer labyrinth, or yeah. And basically they all have advantages and disadvantages, but the bass reflex in studio monitoring, where you want something that's small, powerful, with good SPL, and it's generally what we choose. Closed one has less phase issues, but then it has to be a lot bigger to have the same SPL and the same frequency response. So that's what we choose. I'll just go over this a little bit. I think you explained most of it, but just this is the phase rotation in a three-way speaker. This is brought back. This is all brought back to the front of the speaker. Okay, so there's and this is a log scale. But what you don't want is changes in slopes here, where there are quite a few. Anyway, so there's phase rotation until about 150, and then it's flat through our CPR system. Anyway, the result of all this is if you put in a step response or a square signal that you don't get in the nature, because you'd need an infinite amount of frequencies to fill in all these angles, the square here, but still you do get quite sharp transients on a drum like this. A normal speaker, what will happen is first the high frequencies will come out, the t, then the a will come a bit later, then the t will stop, and then the a will stop. So there'll be the high frequencies and then the low frequencies a bit later. What you do when you compensate phase is you wait until they're all back in phase, and then you start, and they all come out at the same time. So we wait here, this is 1 millisecond, we wait half a millisecond, and all the frequencies above 150 come out kind of at the same time, and then there's a bit of phase rotation in the low frequencies. But again, look at this is 6 milliseconds, which is kind of not much compared to what you get in your room. We'll see that later. So this is just to illustrate what we can do with the AOI system, that's the electronic damping and the phase correction. Okay. One of the key elements is how to get this, and this aligned, so that what comes out is perfectly in frequency and phase. I think you explained a lot of it, but it's what we call over the crossover. And you can play with different things in these crossover filters. You can play with the slope here. That's what order filter you use. And remember that there's not only the electronic filter, there's also the acoustic filter or the mechanical filter from the driver itself. So you tend to use a bit of both of them here, okay, so that they work together. And but you can play with the different slope. You can play with the Q factor. That means, does it go more round or does it go up a little bit and down? You can play with some pre-accentuations here, so you can make it go up and down. So there are lots of things you can play with, and it all depends, but it has to be adjusted to what the driver can deliver, what can come out of here and here, and so that you adjust it all nicely, taking into account all of the characteristics. Okay, so that's one of the key elements I think you explained, and also directivity is important in these crossovers, because ideally what you want is all the frequencies coming out of here and all the and below all the frequencies coming over here, so that you at any single time do you have the same frequency coming out of here and here that will create some interaction that can be positive or negative in some places. But that would mean having an extremely steep crossover, which creates enormous phase rotation and all the rest. So yeah, this is all the things. The directivity is also quite an important thing that comes from here on the crossover. So this is the theory. This is reality, where it's not quite as flat and linear. So this is with the in the box with the vent. So this is the woofer with the port. This is the mid, and this is the tweeter, and it should all be, the total of all of it should be as flat as possible. And you can see that there's lots of little bumps in the driver itself, and you should try and mix and match them so that it comes together nicely. The same with the phase. This is the phase of the woofer, the phase of the mid and the phase of the tweeter, that should all be nicely aligned. We can only hear, you can't hear 5 or 10 degrees of change in phase at all. You have to be, there's a lot of psychoacoustic experiments on how sensitive we are to phase, but big changes we hear, small ones we don't really hear. This is the distortion. So you have harmonic distortion and then non-harmonic distortion. So harmonic distortion is not too much of a problem because it's harmonics of the signal itself. It sounds quite natural, but it still has to be very low, and normally in the range of 50 dB underneath or underneath 1% of the sound is harmonic distortion, and that's the mechanical little vibrations in the box itself. But it has to be low, and in low frequencies there's a lot of energy, so there's more distortion in the lower frequencies. And then what's very disturbing is the non-harmonic distortions that are like rub and buzz, typically a screw or air that's coming out, and that has to be very low. Voila, so that's what we have to do. That's what it looks like in reality, and it's not as simple as just the slide that we saw before. Directivity. So directivity, wavelengths are very different, so also the directivity is very different. Low frequency tends to spread all over the place, and high frequency tends to go in a straight line. And this is just physical. So you can see that a trumpet, so this is, the higher it is, the more directive it is, the lower it is, the more omnidirectional it is. So a trumpet typically is very directional, and when we talk, it's quite omnidirectional. It's much better than most instruments, but still, when I turn around, you can still hear that there's some kind of directivity, but normally it's around the 270 degrees, and in front of that, it's not too directional. But anyway, what we try and do is match the directivity with our speakers, that we get a kind of even directivity that's close to most instruments, so that the sound is as natural as possible. And you can also hear this, when you're walking around the speaker, you can hear either sometimes it disappears completely, or you can still hear parts of it and it sounds more natural. So that's also something that's very important in reproducing sound in a room, especially for listening, hi-fi or at home. When you're in the sweet spot, it's less of a problem. Anyway, just to say that when you do listen to monitors or speakers, first of all, I think it's very important to check the facts. Okay, so do look at the measurements when you look at. Do check all these measurements and see what's been done, okay? Because you have to see frequency response, you have to see phase response, you have to see distortion, you have to see max SPL at different frequencies, you have to look at directivity. So make sure that all this is correct and there's no big accidents along the way. And the other thing is what's also good to make sure is you can print anything in here and then produce something completely different. But what's important is to make sure that what you do receive corresponds. What we try and do is any precision instrument comes with its calibration curve, with its medical device, or a good microphone comes with a calibration curve. So you can ask for a calibration curve to make sure that it corresponds, at least the frequency response. Otherwise, you might be getting anything, or check it when you get home. Then when you check, you can only remember sound over 10-15 seconds. So if you listen to something in one place and the next day you listen to another monitor, it's very, very difficult to know which one, unless it's really your mix in the same room and you do remember it. But normally it's much better to do A/B testing, and if possible, blind. We saw before that what you see influences a lot what you hear. So if possible, blind tests. And what's even better is to do ABX tests. So you have the reference, and then you have A and B, and one A or B is the same as the reference and the other one is different. And then you can see, can I tell a difference and which one do I like better? And if you can't tell more than 50% or more than 75% of the time if A or B is the same of X, you can say there's no difference. Statistically, there's no difference. And that's very simple. Try it with any device and do it. It's the only way of making sure that you're not influenced by what you see and all the rest. Also with a speaker, having a speaker here or here, there'll probably be more difference than you think, just from the position in the room. So it's important to have it at the same place. It's a bit difficult with speakers, but if you're testing a cable or something with one speaker here and with the other speaker here, I can assure you there's more difference from the sound, from the position of the speaker, than from the cable itself. So that's very important. Mono, and when you're testing a speaker, don't take your preferred song and listen to it in stereo in the sweet spot. I mean, that's not going to bring you much information. Mono really is a lot easier to discriminate between speakers in mono. And then use something that's useful and listen to white sound or pink sound. So that's a mix of all the frequencies, and then you can clearly see if there's correlation or not with that. It's much easier than listening to a song. Okay, so listen to white noise, pink noise, and things like clapping is very powerful to be able to understand what's delivered by a speaker, because it's close to a white noise or pink noise, and you can hear each clap in its position in the stereo image. So the stereo image is very easy to identify with this. Voila, so I hope this gives you an idea of what we have to go through to make good monitors or good speakers, and that when you choose it, please try and look at what's been done behind and appreciate it, and do it technically. And when we developed speakers, so there's things you can measure and things that you can't measure that you can hear. So it's very important to listen. But at least what you can measure, you can reproduce in production and everything. So you have to do that right. You have to measure and do that right. Some people say, no, there's no point measuring, it's all about listening. So how are you going to reproduce what you've just listened to if you're not measuring what you're doing? How can you control your production if you don't measure? So you have to measure, at least do that right. Then there's all the things that you can hear that you can't measure. These little bumps in the frequency response give a little character to the speaker. So then you have to go through a lot of listening sessions with different people, different rooms, different type of music, different positions in the room to get it right. Then you say, this is the best I can do with this speaker, we're all very happy with it, boom. Now that's your reference, and then you have to copy this reference in production and do exactly the same one. And there you have to measure, I'm sorry. And you have to measure in an anechoic room, because otherwise you're measuring the room and not the speaker. Okay, back to the room. So now the second thing, as we saw before, second or first most important thing is the room. So what you hear, we've been talking about the direct sound that has to be as accurate as possible because it gives you information on the source of sound. If you have a drum or a piano, it all has to come out like the drum or the piano from the speaker. So you have direct sound, but then you have all the other sounds. You have first reflections that come, and then you have kind of more diffused sound that's been in the room for the time. Okay, so typically you have direct sound, then a bit later you have early reflections, and then what we call the reverbs or the diffused sound. So direct sound as accurate as possible because it gives you information on the source of the sound. Okay, now indirect sound has to be as balanced as possible. You have reflections, you're going to have interactions between the direct sound, between the reflections that are going to give you little accidents in your frequency response curve, which is normal. When I'm talking here, there's lots of reflections. When you listen to a piano in a room, there's lots of reflections. It's normal to have this, and it gives you the sense of the environment you're in. And our brain works well and can understand it quite well. One of the characteristics of a room is how long does the echo stay there. If you're in the mountains, there's no echo. In the mountains, in snow, there's very little echo, so you can feel you're out in the wild. Yeah. When you're in a church, there's a lot of echo for a long time, and you know you're in a kind of confined environment. What's important is that the high and low frequencies, you have the same acoustic environment. So in a church, for example, you can have up to 10 seconds of, we're talking about RT60, that is the time you need to reduce the pressure level by 60 dB from the initial sound down. Okay, and this can be 5 or 10 seconds in a church, so it echoes for a long time. This is how they used to amplify sound or to make sure that people could hear the sound right at the back. The problem with this is that if your acoustic message is very fast, it's going to just get mixed up, and you're going to hear too much reverb and you won't hear the acoustic message. That's why in churches most of music is quite slow and people talk quite slowly. In studios you have to have very fast music also, and all types of music, so you want the reverb time to be extremely short so that you can hear the next sound that's going to come. Very simple. But what's important is that you have the same in the low frequencies and high frequencies approximately. We'll see that it's very difficult, but you don't want to feel as if you're in a cathedral with low frequencies and in the mountains with high frequencies. That is very disturbing, and you get a lot of wrong information in that. Okay, so RT60, the most important parameter in characterizing a room. Now, just a little bit on reflections that are very complicated, and the way we analyze, and that. So this is all psychoacoustics. This is things that are very difficult to measure. You have to ask people what they feel and what they hear. It's not things that you can measure directly. But basically, there's when I speak, there's the first reflections that come a few milliseconds afterwards here, and our brain. You will hear them, but you'll know it all comes from me. So your brain is going to say, these first reflections all come from the same point. So it won't change the image. It'll just change a little bit the amplitude, and it'll change a little bit the tone. Because if it's reflecting off a wall like this, or off a glass wall, I'll have a slightly different timbre in my voice. So that's. But you will analyze it, or you'll see it as one single sound, and that's what we call the Haas effect. You can read, there's lots of information about it, but this is that, and this gives coloration. Then you have all these useful reflections, and this goes from a few milliseconds up to about 30 milliseconds. Below that, the first reflections can shift the image, and you'll hear it. You won't hear it as one punctual source. You'll hear it probably as two, and it'll shift the image. That's why you shouldn't put speakers too close to a wall. You should have them a bit further out. Then, if the reflection, so this is the amplitude of the reflection. If the amplitude is higher than the initial, of course, it's going to give you an image shift, and you're going to focus more on the reflection. It doesn't happen very often, but it can happen if there's in some conditions, especially in public address systems, you can have second sounds that are stronger than the first ones. Then you have these useful reflections that are quite nice, that gives you the sense of the environment you're in. And then you have this reverb time. And this is the echo. If it's too strong, this reverb, then you can hear the echo. And then it's disturbing because you analyze it as two messages and you can't really hear what the first one is. So just to show that all these reflections are very complex, to understand which ones are disturbing, which ones are not disturbing, and which ones are useful to give you a sense of environment or not. Now, room modes. Now I'm just going to explain that there's some frequencies that are much more disturbing than others because they echo for a lot longer than others, and those are room modes. But basically, when a wavelength corresponds to the dimensions of the room, you'll have the echo that come back that'll be perfectly in phase with the initial sound going there, yeah? And then it can come back and forth and just reinforce itself. This is what you call a room mode or a resonance mode of anything. So everything has these resonance modes, a string of a guitar, any type of instrument, and also the air in a room. But basically, so you can have it in phase when the wavelength is, or half the wavelength is the dimension of the room. Then you can that's what you call the first mode. This you all understand quite well, I guess. I don't want to go too much in detail. Then you can have the second mode where you have kind of high pressure, low pressure, high pressure again, and then the third mode, and so on and so on. So here I'm also showing pressure, and so you have sound is pressure going up and down, as we saw. And that's what we hear, that's what we reproduce, that's what we get in our microphones and what we measure. But there's also velocity that goes, that's the molecules go back and forth. With the pressure going up and down, the molecules go back and forth. And that's what we show here. So of course, on a wall, a rigid wall, this velocity is zero, it's stopped, and the pressure is highest. So that's when you get the echo that comes back. And when it's perfectly in phase, you always have the high pressure places at the same place. Yeah, so you can, in a mode here, this is probably 10 meters long, so that's 35 hertz. So you'll have 35 hertz is the second mode. The first one will be about 17 hertz. So you'll have high pressure here, and go down, and high pressure over there again. So they're very long wavelengths. Anyway, an example of room that's 7 times 5 to 2.5 meters. The frequencies here, the room modes are 25 hertz up to about 140. And in most rooms, studio-like, the room modes about in that range, between 15 and 150 hertz. So here we can see, so you have different room modes, this way, this way, this way, that you can see length, height, and width. And then you can have second ones, and second room modes or combinations of two of them. So you can have a mode that goes a bit round like this, or different ways, okay? But you have lots and lots of them. And this is a perfect shoebox, and you can see that the pressure is there's a nice pattern of high pressures and low pressures, and it's all very easy to understand. Unfortunately, it's never like that, and most rooms are performed very differently. Just one thing you have to understand also, it's important to understand, is that the first modes, the actual modes, are much more disturbing than the others. Sound loses energy a little bit going through the air, but mainly when it bounces off something, it'll lose some energy. So the more bounces there are, the more it'll lose energy. So this one will decay, or this one will decay faster than this one and faster than this one. So these ones tend to be the most disturbing, the ones that will echo for a very long time. So yeah, this is an example of a room. So here you have modes at 40, 49, and 68 hertz. And you can see the pressure distribution here, where you have high pressure here, the disturbing high pressure in the listening position here, and high pressure there. And then another frequency can be completely different, and another one completely different. So basically, you're disturbed by three modes here that come from very different positions, but often the corners contribute more than anywhere else. So just keep in mind that the corners are quite important here. Then these room modes are, well, they're quite a problem because, well, first of all, they echo for a lot longer than the others. So instead of having a RT60 of like 0.3 seconds for most of your frequencies, a lot of the room modes can echo for 0.7 or up to 1 second. It's disturbing. And you're hearing the room modes while they're not really there. Plus they're low frequency, so they tend to hide by masking effect the higher frequencies. And then also you'll get a very uneven pressure distribution in the room. When all the sound is diffused, you have an even pressure distribution. You can sit anywhere in the room, you'll have the same sound. In the low frequencies, we can do a few tests afterwards, you move around and the pressure is very different. So whether you sit in one position or another, or even just moving by 20 centimeters can change it a lot. So they're very disturbing, these room modes, and we want to get rid of them. So you should think of the room being behaving in a diffused way in the high frequencies, and then a modal way in the low frequencies. Yeah, and then there's a transition that's called the Schroeder frequency that gives you an indication of above which frequency the distribution is diffused and below which it's modal. So here you see the same room we had before, and you see the different modes. Yeah. The 1, 2, 3, the second mode in the one way and all that. And the Schroeder frequency is here for this room. And it shows that above that, there's so many different modes, they get mixed up with a diffuse sound, they're not that disturbing. But below this, they are disturbing. That's what this Schroeder frequency, and they're easily 30 modes. So just remember that there are many, many modes that are disturbing, not just one or two in the room, but not in all the positions in the room. So all these room modes, first reflections, diffusions, they all come from one physical process, that is the reflection of the walls. So if you want to control your room, you have to control the reflection. So we'll look at how we can, different ways of controlling reflections. So first thing is, I explained before the difference between the pressure that goes up and down and the velocity. Yeah, this we understand. Of course, they're out of phase. Energy conservation dictates that when the pressure is higher, the velocity is low, and vice versa. Then, when the sound wave reaches a wall, Well, part of it is reflected, and part of it is absorbed, and part of it goes through. Okay, this I think you all understand. And when we're looking at a room, when we're inside a room, we don't really bother whether it's absorbed or transmitted further on, although the neighbors will probably notice. We look at just what comes back in the room and what stays in the room, and we'll measure the ratio between this and this to say whether a material is absorbent or not. And if it's 100% absorbent, we'll say it's got a alpha Sabine of 1, and if everything's reflected, it's got an alpha Sabine of 0. This I think you're all familiar with. And basically, 1 square meter of absorbent with a Sabine alpha Sabine of 1 is the same as just opening 1 square meter and all the sound goes out, nothing comes back. Okay, and you can get to things that are quite close to 1 with just passive absorption. We'll see that. This you're all familiar with. So just think of the alpha Sabine as being the equivalent absorption area of a perfect absorber. So yeah, just analyzing reflections. So you have pressure sound going through the air at 350 meters per second, but you also have this velocity going through. So imagine you're swimming in the water, you have the waves going up and down, that's the pressure, but you also feel as if you're going back and forth, and that's the velocity. Now think of the velocity, so it's a wave of velocity coming like this, and when it reaches a wall, it stops. So where does this energy go? It can only build pressure. Okay, like the waves crashing against the wall will crash up, creating pressure that will create the reflection. So that's basically how a reflection happens. And there's different ways of treating or controlling these reflections. First of all, you can change the angle. So you're not absorbing more, but you're going to reflect in a different direction. That's one thing you can do. And the other thing you can do is you can slow down this velocity. Okay, so that when it reaches the wall, it's stopped. So basically you have to slow it down before it gets to the wall. So that's what we do with porous material. And the other way you can do it is to move the wall in frequency or in phase with this velocity. Is that all? We'll go in a bit more into detail with those, but those are the 3 ways you can control your reflections in a room, or any reflection. So diffusion, so here basically is the diffusion. So this is here, well, first of all, instead of having the reflections all at one frequency coming back and being disturbing, well, you have different, so you're distributing the frequencies that come back, the filters. Yeah, plus you get a bit of reflections here. So diffusion works very well when you have, for example, relatively high frequencies, and in first reflection points, it works very well. Okay. And then you can have different angles, and instead of all the sound coming at the same place, you have different angles, so some of it is going in different directions. That's diffusion, and there's a lot of diffusers on the market that all work very well, and you can also use books and things like that in a bookshelf that also have some effect. Now, so that's changing the geometry of the wall. Now, slowing down the speed. Here you see the speed and the different modes, and you can see that if you want to slow down the speed so you use porous material, so the energy is absorbed by the friction of the molecules inside the porous material. But to do this, to absorb as much energy as possible, you should have to do it where the speed is highest. So you have to do it here, here, or here. So typically, a quarter of the wavelength of the frequency away from the wall, which for the first room mode is in the middle of the room, by the way. That's a bit disturbing. But anyway, so you need either to position the porous material inside off the wall, or you can have it thicker. And typically when you buy any porous material, rock wool or anything like this of different thicknesses, it'll work very well, and then below a certain frequency, the efficiency is going to drop down. And typically this is around a quarter of the wavelength of the frequency you want to absorb. And yeah, just a few dimensions, 20,000 hertz, 4 millimeters of absorption will work. 20 hertz, you need 4 meters if you want to get to the highest efficiency. So yeah, it takes up a lot of space, this porous material absorption. Yeah, so here we've got the wavelength. So this is the frequency from 750 hertz down. So this is the wavelength, and a quarter of the wavelength is here, and this is the thickness of insulation you would need to treat it properly. And you can see that most of the problems, well, it's quite easy. You're up to kind of 20, 30, 40 centimeters down to 200 hertz, but most of the problems are below that. So this is a good explanation that shows that where the room modes are, porous material is not very effective, or you need very, very big dimensions. When you buy a bass trap that's about this size, forget about it absorbing 50 hertz. It's just not going to work. You need something much bigger. Okay? So this is, one thing again about porous material is what I explained is for the first echo. But when you do have a RT60 of 0.3 seconds, so the resonance time is 0.3 seconds, your sound will have traveled 100 meters. So it will have hit quite a few times the different walls. So it will have reduced quite a lot. So even porous material that's a bit of porous material, with time or with the RT60, it'll reduce the SPL quite a bit. So very useful also. Now, the next way of treating your reflections is to get the wall to move. So this we can do with resonators. Passive resonators, like any of these panels or glass, will move at a certain frequency. And it'll move very easily on its own resonance frequency. So you can use panels with a resonance frequency that's adapted to the frequency you want to absorb. And you can use a panel like this one here, or you can use a Helmholtz. You know what a Helmholtz resonator is. It's again mass on springs, so it's some air, a mass of air in a volume of air that acts as a spring. So these also work quite well, but they only work on their resonance frequency very well. It's very difficult to get them to move properly and absorb on other frequencies. So they tend to have to be, if you look at the alpha Sabine, they tend to be very efficient on a certain frequency, their own frequency, but not outside. So either they've got a very high Q factor and they can absorb very well, but only on a very narrow bandwidth, or they absorb less well on a wide bandwidth. This I think you're familiar with, and if you've ever tried to tune and position resonators, you know how difficult and complicated it can be. But these they do work also very well. So here again, this is just showing the pressure, the waves. So the water, you can imagine the water coming here, and as the water comes, you move the wall, and this will move. This will absorb this energy. This I've explained. So now we move on to active absorption. And this is the same as passive absorption, the resonators we saw. But instead of the resonator only moving on its resonance frequency, you are going to put a little engine behind it to make it move at the frequency you want it to move. So this is exactly what we do here. I'll probably come back to this one later. Okay, so we make this move, but of course in acoustics it's very difficult to get a whole panel move at the speed, frequency and phase you want it to without creating any other sound. It's very difficult. But what we can do, instead of making a big wall move, you can make a small portion of it move, but you move it further, displacing the same amount of water or air. Okay? So imagine these are waves. You have to move this wall back and forth to avoid the waves crashing and creating echo. But instead of moving the whole wall, you displace the same amount of water in a smaller area. Yeah? And you can imagine here how a small area can have an effect much bigger than its area, because you're pulling water from all over the place. So you can imagine displacing the same amount of water here than here, that this little surface can be as effective as all this. So this is what we try and do. So here, of course, you're accelerating. The speed is higher. So this velocity is much higher. And the ratio between pressure and velocity is much lower. Okay? So this is the acoustic impedance is very low here. Much lower than anywhere else. And this is how we try and do it. Anyway, this explains a bit more. Is what we can do is we can measure the pressure that comes here, or the level of water, and says at this height of water, I have to move the piston this far back or forward to avoid any echo coming back. You understand the principle? No? What we're trying to do is this speed is coming against the wall, and we want to move the volume to create room for all of this speed that's coming here. So you're basically, if you're moving back, forget about the tube for the minute, but you want to displace the amount of water there is in this wall so that it makes room for the speed that comes. So you're absorbing the wave. A little bit like when Rafael Nadal absorbs a ball, he's sort of making room for it and he's absorbing it. Yeah. So this is the same mechanism, but so it's a quantity, a volume of water that you have to move and make space for it. And this volume of water, you can make it over a big surface or a smaller surface. And here we're making it over a smaller surface by moving it, by having a much bigger path and displacing much further. And here we're increasing the speed because the same amount of water has to go through this surface than this surface. So the ratio of speed is the same ratio as the surface. This is quite basic, I think, in hydrodynamics and things like this. Probably not in acoustics, but it's the same principle. Anyway, so this is what we do in our device. That's the AVAA. Is we measure the pressure of air, and this is a normal microphone. And then we say for this pressure, to avoid any reflections, we have to move back or forward so much. So we're basically increasing the speed here. We're lowering the acoustic impedance in front of it. Now, to be accurate, you can't put this float here because you'll have a lot of interference and you're going to be wrong in some places. So you have to put it as close as possible for it to be accurate. That means the time you have to be in phase is very, very short. And in our AVA, we have about 4 or 5 centimeters. So that's the time you have to get your movement of counter-reaction absolutely accurate in time. That means that any conversion into digital is going to slow it down, and analog technology is a lot faster for that. So we did develop quite a few prototypes before getting it right, and we developed digital technology is great because you can change the filters very easily, but once you get it right, you can fix it in analog technology, and it's always, in this device here, it's always more stable and more efficient. So we use analog technology for this. Anyway, this is how it works. Then, so we have a microphone, then we have all our conversions, and then we drive this, it's a speaker that's behind it, that we drive as a source of velocity and not a source of pressure like we do in sound. We have also this micro-perforated grill here that goes around it, and what you should think of is it changes some of the pressure into speed. The way you have a bucket, if you have a bucket of water with pressure in it, it's full of water, so at the bottom there's no speed but there's pressure. But when you punch holes in it, the water will come out with speed but no pressure. So you should think of this as a bucket of water. You're pouring water in it and there's pressure at the bottom, but what comes out is only speed and no more pressure. So we're measuring the pressure outside and we're saying for this amount of pressure we have this flow of air going in and out, and we have to compensate for that flow of air with this membrane going back and forth. So we're driving this membrane to keep a pressure of 0 in here. It seems simple, but we spent at least 20 years trying to get it right. Anyway, the effect of all this is you have your AVA, and you'll tend to put it in the corner because that's where there's the most effect. And you should think of it as having, here you have an impedance of 100 Pascal per meters per second, this pressure over speed. And the pressure, this impedance goes up over about 1.5 meters and to 400 Pascal per meters per second. And that's equivalent to the acoustic impedance in the free field outside. So you should think of this when you're looking at it. You have a surface here that's the portion of sphere around the device that has an acoustic impedance of 400. And that surface is the equivalent absorption area of a perfect absorber. So the only thing we're doing with this device here is we're imposing a very low acoustic impedance of 100 in frequencies between 15 and 150, which is where you have most of your room modes. Now, if you put this device here or here, the effect on that room mode is going to be very different. If you put it in the corner, you probably get rid of the room mode. If you put it in the middle, it'll have no effect because there's no pressure, so it has nothing to absorb. Okay, a few examples maybe. We can demonstrate it afterwards, so it'll be a lot easier to understand. But basically, if you have this situation we saw before, you'll put them in the corners and you'll affect all the three modes here that will reduce significantly the pressure in the middle. Now, in terms of equivalent absorption area, well, this is a combination of theory plus an enormous amount of measurements in different rooms, and you can get to, so the device is 0.2 meters, square meters, and you can get equivalent absorption areas up to 8 square meters. So yeah, you can go up to 40 times. So alpha Sabine, you can't talk of that, but an equivalent absorption area 40 times bigger than the device. So this is in very high pressure areas, and if you put it in lower pressure areas, kind of here. Or in some places, it can have no effect at all if you're not in a pressure area. But this shows sort of how effective it is, And then it continues absorbing above 150 hertz, but the efficiency goes down quite a bit. And we could go higher in frequency, but that means you'd have to make things a lot smaller. The equivalent absorption area would be smaller also, so the economic value would also be a lot smaller, and also this is really the range where we have most disturbing room modes. So we'll do demos later. But this is the first tests kind of we did, so you put it in the corner, and we were comparing it to a big bass trap like this. So this is the room with nothing in it, and you can see that it's, so this is, I mean, it's like a waterfall, but you can see it from the top, yeah? And the time goes like this. So you can think of here, you've got your kind of RT60 that's around half a second. That gives you the characteristics of your room. But you can see some of the modes are longer. There's a lot more pressure stays in this area, and then there's holes here. Okay? And then you can put those passive bass traps in, and you can see that you can affect a bit of this area here and get rid of a bit of this energy here. So I would say this one's not perfectly tuned. You'd probably want to move it a bit further here and also try and affect this hole also. So with the AVAAs put in, well, we get this kind of result where we've taken a lot of energy out of here, a lot of energy out of here. We've smoothened it all out quite a bit, okay? So here you have a much more even response time in your room than you did here or even here. That's one of them. This is the example we saw. So this is Andy Hong in his room in the US. So this is his room. So you have the frequency response, and then so you can see it's quite even. Well, it's not, but I mean, the resonance time should be about here, and you have these two resonance frequencies that stay on a lot longer. And when we turn them on, well, you reduce them a lot, and it evens out a lot of the frequency response time. Again, trying to get this flat is extremely difficult because you'd have to do it in an anechoic chamber. But what's important is to not have big differences in time. So, just the problems in room modes is that you, well, the first thing is it reduces the RT60, yeah? So it doesn't, the room mode will echo less, and it'll be, so all this time it's not echoing, it's also not masking higher frequencies. Then the pressure distribution in the room will be a lot more even, and also as you have less indirect sound compared to the direct sound, is that your location of the low frequencies will be much more defined from in the stereo image. So this is what the first users told us. Key takeaways. Yeah, I mean, another great advantage is that it's mobile and you can move it around. We have one of our customers just next door. He has a few of them, so he puts them in his recording room When he's finished recording, he puts them in his mixing room or his mastering room. When he does recordings off-site, he takes them with him and does recording off-site. Just for your information, we also have sold some that we put in boiler rooms and heat pump rooms where there's the hum of the machinery is disturbing the people above, and that gets rid of it properly. In the hospital in Geneva, they have some in all their technical rooms. And in flats in London built above the underground, so there the sound comes up in the solid walls and then generates noise inside the room that excites the room modes. And we got 6 dB reduction on these modes in these flats in London. But most people buy them for studios. So here, the first people we sent them to test were Bobcat, who bought some, Andy Hong, who bought some, Barry Rudolph, who bought some. But Andy Hong, I think, summarized it perfectly by saying there was not enough boo in the bass, but way too much oom, clouding the overall image by masking effects. Once we turned on the AVA, we could all hear the boom clearly and everything else in the mix too. So that's basically summarizes how it works. Okay, I hope I've given you a bit of an overview of what sound is, how important it is to have very accurate direct sounds, and how important the room is. I'll just show you a little bit about our company now. So we started making speakers 40 years ago. The company was founded by Alain Roux, who's now retired but still active. And we started making PSI audio passive speakers that we still repair, speakers that are 40 years old. So normally it's the suspension that wears out, but we can repair those and they go back out for 30 years. Sustainability starts by making sustainable products. Then we did a lot of PA equipment, big things, big basses and all that. And then 88 we started manufacturing Rowan. That's a brand of hi-fi speakers that's only sold in Switzerland, but we've been manufacturing those for 25 years. Then in 92 we developed active speakers for Studer that we built for Studer. I think you've probably already seen these ones around. So we made these until they were acquired by another group that didn't want Studer to sell speakers anymore. So we relaunched PSI, our old brand, in 2003 that we sell now. So yeah, for over 40 years, 41 years experience, 25 years in active technology. This is where we're based. We love having visitors, so please come and visit if you're ever in Switzerland. So our technology, we explained all this, but first thing is that everything has to be, you can't take a driver, a magnet somewhere, an amplifier somewhere, all put it together and think it's going to be perfect. It all has to be designed perfectly together. The box, the port, the amplifier, the membrane, everything has to be designed as a system. Digital or analog? Big question. We looked a lot at we still look always at the advantage of digital technology. We find, digital technology is fantastic if you have to memorize information. You don't need to have long tapes of magnetic tapes, okay? So it's great having all that digital. It's great if you want to process information. But if in a speaker, everything you do is going to stay in the speaker and it's going to be the same during the lifetime of your speaker. So you can fix that in analog technology and you avoid, first of all, double conversion. You avoid any chopping up of the signal again. You avoid latency. So for us, it's a lot easier to do it, to keep it all analog. The difficult thing about analog technology is that all the filters and everything you make with components, and all these components have to go together. So you have to minimize the amount of components, and then you have to have an extremely tight control of each component that you put on so that they all work together. But that's our speciality, and we've been doing it for a long time, and we know how to do it. The other thing is sound engineers. They'll do all their work in digital on the digital domain. That is normal. Then sooner or later, they'll go through a converter, and you'd like to choose your converter, and it's one of the key elements of in your process. You don't want to have another double conversion in the speaker that you don't control. So that's also something to think about. The advantage of digital also is that you can change filters like this. on a keyboard. So you can do anything, but you have the same physical problems as with analog filters. You have the latency, phase rotation, and all the rest. That you can't get rid of that. Amplifiers we use are Class G amplifiers, Class GH amplifiers. Did you explain a little bit the different? We also make amplifiers for precision mechanical industry in Switzerland. So there's lots of other industries than the audio industries that use our amplifiers. There's a big international company in Switzerland. They have at least 150 people in R&D, and they couldn't get what they wanted to get with digital amplifiers. So they asked us if we could do a prototype. We did a prototype. They love it. They give us royalties, and they use it everywhere. Basically, what they have is they have tables that have to move and do sort of soldering for wafers. So they have to move very fast over a few meters, but then stop very accurately and amplifying this signal that has to be quite strong, but also has to be extremely accurate. They found very difficult. AOI we talked about, CPI we talked about. That's our technology. Of course, we use a lot of digital technology to develop our stuff. We're a small company. We don't have enormous volume, but we also like having a complete control over all the production process, and all the cabinets are handmade, hand-painted, and it seems very simple making a cabinet, but there's ways of making it properly, and there's ways of making it where it'll break, or it'll have cracks in it after a few years, or it'll vibrate, so it has to be done properly. The paintwork also has to last for 30 years. This is us making the tweeters. So tweeter of the A25, we can't find anything like this in the market, so we have to make our own. Cost us a fortune, but no other solution. So we do everything from the winding, from magnetizing the magnets and everything. And with the same technology, we've also made seismographs that measure vibrations in bridges. So a lot of bridges in Europe use our seismographs. Just a hobby business. We don't make money out of that. So analog technology, again, we're small, and we like keeping a continuous view of the whole process. So we do it all by hand. It's and soldered by hand. And the advantages is we're extremely reactive. If we have to change something, we can check everything. We can repair everything very easily. This is all the assembly, all done by hand, cleaning, last inspection. And if the role of a speaker is to transform an electric signal into an acoustic signal, well, you have to check the speaker to make sure it does that job. And that's it. So you inject a signal, and you measure what comes out with a microphone, and you want to measure what comes out of the speaker and not from the room. So you need a room that's got no echo. So you need an anechoic room, and you have to do it. So we do this for every single speaker, goes through here, and every single one gets its frequency response curve. We don't just check the frequency response, so that each one is calibrated properly here, and you get the frequency response, phase response, harmonic, non-harmonic distortion. Anyway, as a result of that, we're extremely proud of every speaker that leaves our factory, and we have very good references around the world. What we love best are blind tests. If people want to do a blind test, we'll say, yes, please go ahead. Blind test, a good protocol, always works. And places like the Bolshoi, talked about Boris Blanc, our national hero from Yellow. I don't know if you know him. King's College in Cambridge, NHK Tokyo, Tim Rowe, Tileyard Education, National Film and TV School. Bought 80 of our speakers last year or 2 years ago after testing all the speakers on the market. IRCAM in Paris, Research Center. Many Montreux Jazz Heritage Lab. Voilà. So I think I come kind of to the end of the presentation. I didn't write this, but
Questions.
Any questions at this stage? We'll be here all day, so any questions you have, or if you want any explanations, and we're going to demonstrate the speakers, or you can play with them here, and we also do a demo of the AVA, and you'll see that it's in maybe 30 seconds, you'll understand a lot more than what I've been trying to tell you here, but at least you'll understand the principle that it's basic physics. It's not anti-noise, it's absorption. That's the first thing you have to understand. It's not sound cancelling, it's absorption. And it's pure physics. It's not psychoacoustics either. It's just pure physics. Any questions at this stage? Or in Spanish to Robert? Anyway, I'd like to thank everybody here because it's been everybody's been extremely welcoming and extremely helpful getting everything up here. And yeah, here you see our website and the website of our distributor in Spain, Swiss Audio. Thank you very much.